Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 1st, 2025, just yesterday. It delivers a real-time 3D reconstruction system that reaches a surface reconstruction error of 0.6 centimeters on benchmarks like Replica and ScanNet++, over 20% more accurate than previous Gaussian splatting methods, while still running at about 24 frames per second. The paper is titled EGG Fusion, Efficient 3D Reconstruction with Geometry-Aware Gaussian Surfel on the Fly. And as we will see later, the results are really impressive for both accuracy and speed. Also, the authors shared the GitHub repo for EGG Fusion. There you will find the official implementation along with a short README that explains the real-time 3D reconstruction pipeline and its geometry-aware Gaussian surfels, plus some supporting assets. The repository already positions the code within SLAM and surface reconstruction workflows. Alright, after the code overview, Figure 1 gives a visual taste of what EGG Fusion delivers on real scenes. The left column shows the input, RGB, and depth views for three objects: a bag, a hydrant, and a stone. The central panels display the reconstructed scenes and the high-confidence surfels, which highlight crisp geometry and clean surface normals. The right panels compare novel view synthesis, where the proposed method keeps objects sharp and stable, while RTG-SLAM and SPLATAM look noisier and more blurred. Well, Figure 2 explains how EGG Fusion actually runs frame by frame. The left block illustrates camera tracking, where sparse feature matches give an initial pose that a dense alignment stage then refines using the current surface. Below that, the color and depth images form the RGBD sequence that feeds the system. On the right, the scene mapping pipeline initializes Gaussian surfels, fuses repeated observations with an information filter, and optimizes them jointly with color, depth, normal, and geometric regularization losses, so the reconstruction stays both sharp and stable. So, after the method pipeline in Figure 2, Table 1 reports how well different systems track the camera on the replica dataset. The metric is ATERMSE in centimeters, which measures how far the estimated camera path drifts from the ground truth path. Competing methods vary widely, with some averaging over 6 centimeters of error. RTG-SLAM already does well at about 0.18 centimeter average. Ours slightly improves that to about 0.17 centimeter, while also giving consistently lowest or tied lowest error across almost all individual scenes. Alright, Table 4 shifts from tracking to image quality and reports rendering performance on the ScanNet++ dataset. The table shows that the proposed method achieves the best peak signal-to-noise ratio and structural similarity for both novel and training views, so rendered images look sharper and more faithful. The learned surfel model also keeps the learned perceptual image patch similarity low, which means fewer perceptual artifacts compared with .SLAM, SPLATAM, and RTG-SLAM. So, while Table 4 focused on image quality, Table 3 turns to 3D reconstruction accuracy on Replica and ScanNet++. The table lists accuracy, completeness, and their 3 centimeter ratios, so it measures both how close points lie to the true surface and how fully the surface is covered. The proposed method achieves sub-centimeter accuracy in the point-based setting and reaches about 100% accuracy ratio, clearly ahead of .SLAM, SPLATAM, and RTG-SLAM. That combination of low error and high coverage shows that the geometry-aware surfels recover surfaces that are both precise and dense. Okay, while Table 3 highlighted accuracy, Table 5 compares time and memory on the Replica Office 0 scene. The table shows that the proposed method keeps mapping time per frame to about 0.07 seconds and reaches around 24 frames per second, clearly ahead of the baselines. Memory usage also stays lowest at roughly 1.8 gigabytes, even though the model size is mid-range. Tracking time splits into sparse pose estimation and dense alignment, which together remain competitive with real-time systems like RTG-SLAM. EGG Fusion shows that geometry-aware Gaussian surfels can deliver sub-centimeter, highly complete 3D reconstructions while staying truly real-time on modest hardware. That mix of accuracy, robustness to noisy depth, and efficiency makes dense mapping far more practical for robots, AR, and 3D capture tools. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.